strings over a finite alphabet. Now we are going to study problems in which we are not simply arranging certain objects, knowing how many times we can use each object, but rather construct the strings or words from a finite set of symbols, which we call a finite alphabet. We will not require that each symbol occurs a specific number of times, though we may require that each symbol occur at most once. Theorem 3.6. The number of k-digit streams one can form over an n-element alphabet is n to the k. Proof: we can choose the first digit in n different ways. Then we can choose the second digit in n different ways as well, since we are not forbidden to use the same digit again, unlike in case of permutations. Similarly, we can choose the third, fourth, etc. kth element in n different ways. We can make all these choices independently from each other, so the total number of choices is n to the k. Example 3.7. The number of k-digit positive integers is 9 times 10 to the k minus 1. Solution: there are two ways one can see this. From theorem 3.6, we know that the number of k-digit strings that can be made up from the alphabet 0, 1, 2, 3 until 9 is 10 to the k. However, not all these yield a k-digit positive integer. Indeed, those with first digit 0 do not. How many are they? Disregarding their first digit, they are k-1 digit strings over 0, 1, 2, 3 until 9 with no restriction. So theorem 3.6 shows that there are 10 to the k-1 of them. Therefore, the number of k-digit streams that do not start with 0, in other words, the number of k-digit positive integers, is 10 to the k minus 10 to the k minus 1, which is equals to 9 times 10 to the k minus 1 as claimed. Alternatively, we could argue as follows. We have 9 choices for the first digit, everything but 0, and 10 choices for each of the remaining k minus 1 digits. Therefore, the number of total choices is 9 times 10 times 10 and so on times 10, which in summary is 9 times 10 to the k minus 1, just as in the previous argument. Before we discuss our next example, we mentioned a general technique in enumeration, the method of bijections. Suppose there are many men and many women in a huge ballroom. We do not know the number of men, but we know that the number of women is exactly 253. Suppose we think that the number of men is also 253, but we are not sure. What is a faster way to test this conjecture? We can ask the men and women to form man-woman pairs. If they succeed in doing this, that is, nobody is left without a match, and everyone has a match of the opposite gender, then we know that the number of men is 253 as well. If not, then there are two possibilities. If some man did not find a woman for himself, then the number of men is more than 253. If some woman did not find a man, then the number of men is less than 253. This technique of matching two sets element-wise and then conclude in case of success that the sets are equinumerous is very often used in combinatorial enumeration. Let us put it in a more formal context. Definition 3.8. Let x and y be two finite sets, and let f which maps from x to y be a function, so that 1. If f of a equals to f of b, then a equals to b. And 2. For all little y in capital Y, there is an little x in capital X, so that f of x equals to y. F of a little x equals to little y. Then we say that f is a bijection from x onto y. Equivalently, f is an bijection if for all little y in capital Y, there exists a unique x little x in capital X, so that f of x is equals to y. In other words, a bijection matches the elements of x with the elements of y, so that each element will have exactly one match. Definition 3.9. Let f which maps from x to y be a function. If f satisfies criterion 1 of the definition 3.8, then we say that f is one-to-one or injective, or is an injection. If f satisfies criterion 2 of definition 3.8, then we say that f is onto or surjective, or is a surjection. Proposition 3.10. Let x and y be two finite sets. If there exists a bijection f from x onto y, then x and y have the same number of elements. Proof. The bijection f matches elements of x to elements of y. In other words, it creates pairs with one element from x and one from y in each pair. Say f created m pairs, then both x and y have m elements. The advantages of the bijective method are significant. Instead of enumerating the elements of x, we can enumerate the elements of y if that is easier. Then, we can find a bijection from x onto y. Let us illustrate this by computing the number of all subsets of m braces without resorting to induction. Example 3.11. The number of all subsets of an n-element set is 2 to the n. Solution. We construct a bijection from the set of all subsets of an n-element set into that of all n-digit streams over the binary alphabet, the set 0, 1. As this later set has 2 to the n elements by theorem 3.6, it will follow that so does the former. To construct the bijection, let B be any subset of m braces. Let f of B be the stream whose ith digit is 1, if and only if I in B and 0 otherwise. This way, f of B will indeed be an n-digit word over the binary alphabet. Moreover, it is clear that given any string S of length n containing digits equal to n0 and 1 only, we can find the unique subset B, which is a subset equals to n braces for which f of B is equal to S. Indeed, B will precisely consist of the elements I in n braces so that the ith element of S is 1. Example 3.12. A city has 10 recently built intersections. Some of these will get traffic lights, and some of those that get traffic lights will also get a gas station. In how many different ways can this happen? Solution. It is easy to construct a bijection from the set of all distributions of lights and gas stations onto that of 10-digit words over the alphabet A, B, C. Indeed, for each distribution of these objects, we define a word over the set ABC as follows. If the ith intersection gets both a gas station and a traffic light, then let the ith digit of the word that we are constructing be A, even if only a traffic light. Then let the ith digit be B, and if neither, then let the ith digit be C. Clearly, this is a bijection, for any 10-digit word can be obtained from exactly one distribution of gas stations and traffic lights this way. So the number we are looking for is, by proposition 3.10, the number of all 10-digit words over a 3-digit alphabet, that is 3 to the 10th. Theorem 3.13. Let n and k be positive integers satisfying n which is greater than or equals to k. Then the number of k-digit streams over an n-element alphabet in which no letter is used more than once is n times n minus 1 and so on times n minus k plus 1, which is equals to n factorial over n minus k factorial. Proof. Indeed, we have n choices for the first digit, n minus 1 choices for the second digit, and so on, just as we did in the case of factorials. The only difference is that here we do not necessarily use all our n objects. We stop after choosing k of them. The number n times n minus 1 and so on times n minus k plus 1 is sometimes denoted n with subindex k. Example 3.14. A president must choose 5 politicians from a pool of 20 candidates to fill 5 different cabinet positions. In how many different ways can she do that? Solution. We can directly apply theorem 3.13. We have a 20-element alphabet, the politicians, and we need to count the number of 5-letter words with no repeated letters. Therefore, the answer is 20. Choose 5. No, it's 20 braces with a sub under 5, which is equals to 20 times 19 times 18 times 17 times 16. If the candidates are all equally qualified, it may take a while.